My name's James Reinders, and some of you may have read some things. I have the privilege quite often of announcing some wonderful things Intel does. I've spent the last 23 years at Intel working in HPC, and I have done a lot of things. I'm a compiler engineer. I love to be really close to the metal, and somehow that means I do software and hardware, so I've kind of gone back and forth, usually working on the software side, but quite often working on the architecture of things. So I was involved in the architecture of the P6 chip, the Itanium processor, P4, and I'm involved heavily with the NITES program, the mic. I was also one of the architects of ASCII Red, the first teraflop machine in the world. Great privilege to help build a machine that was #1. I was on a machine that was only reached #2. I think that this architecture is going to give us the opportunity within the next decade of building a #1 machine. That's not an official Intel position. Our goal is to build a lot of machines that a lot of people use, and you'll see that with the Xeon, which currently the highest ranked Xeon machine is #4, which is pretty high, but you'll see, things like 70-some% of the machines in the top 500 are based on Xeon. That's really Intel's goal, and I think you'll see that's our goal with the mic architecture as well, is to be an architecture that's extremely widely used. Personally, I'm looking forward to seeing a #1 machine with the mic architecture, and I would prefer that also be the first exaflop machine, but again, not an official Intel goal by any means. Anyways, having fun. I think we've covered the fact that the design point for mic is to be highly parallel, power efficient, but not give up that programmability. And you see the flexibility of the machine. So nice pictures we've drawn about how this all wraps together. But let me talk about what we're doing with tools. So in the tools space, certainly we've got the Intel tools, our compilers and our libraries and so forth. And then we also have a version where you take all of those tools and add MPI tools on top of it. And we've got that as well. All of these, Xeon and Xeon Phi. It's an easy story. And that's where we're headed. But we're also working with a lot of other vendors. So let me run down where we're at right now. The ones that are in bold on here exist today, and people on the program have and use. The ones that aren't in bold don't really exist to people in the program, or at least not uniformly, although with a little bit of initiative, some of them are accessible. Python, for instance, I didn't bold it. There's some postings on our internal network, actually our network with customers, that someone's patched Python. I know customers that are running Python code. Intel had nothing to do with, well, other than building the machine and having the operating system, nothing to do with creating the Python. Other ones that aren't bolded on here, like RogueWave's Total View and Alinia's DDT and Scale MP's and VSPM. These different things, they were demoed at ISC. They exist. They haven't been given out yet. So we've got a lot of partners doing neat things. GCC, we ported GCC and we released all the mods to it, but it's useless for applications because it doesn't support the vector instructions. Now, that was, we ported GCC to build the kernel and build things like that, and does a great job of that. GCC's vectorizer is not up to the task of this type of an advanced vector architecture. And what I mean by that is we could have put the vector instructions in, but you would probably consistently see half or a quarter of the performance with it on applications, and we're pretty sure that that's not nearly enough. Vector instructions these days have gotten wider and wider, and one of the implications of that is that they get harder to use for compilers automatically unless you take advantage of something we call masking operations. So the AVX and especially our new mic 512-bit wides have very advanced masking techniques. That way a compiler can be running a loop that doesn't necessarily line up exactly on a vector start and stop, and isn't exactly a multiple of the vector, and it can use a mask so that when it's starting and stopping the loop, that the mask controls that you don't operate on the entire length of the vector. GCC doesn't have that capability today. Very few compilers do. I believe Intel's is probably by far the best at this. And adding that capability to GCC will happen someday. It's something we hope to work with on the community, but that's why GCC is not there. We've got GDB, of course, threading building blocks. I was warned not to become an advertisement. I have an attitude about all of these, and I'm happy to share it. Actually, all four of us from Intel, best thing in the world is ask us questions. We'll tell you like the official stance and the fact that Intel wants to enable everything. But if you ask me a different question, my personal opinion on things, I'll tell you which ones of these I think are worthwhile and which aren't. Actually, almost everything on here is worthwhile because OpenCL is not listed. But I can describe, I have friends that love OpenCL. I can describe why OpenCL is important in some places and why I would have doubts on this type of architecture. And hopefully I can give you a balanced answer on that. TBB, which I think the world of, I guess I wrote the book, so it's awesome. We've got people with FFTW and IMPitch ported. Let's see. Anyways, just a lot of software, and this is just today, and this is a long ways before the launch of the product, or a long ways, depends on how you think. I guess it's still before launch on pre-production parts. For instance, the RogueWave folks, TotalView, when I first talked to them about porting to our architecture a year ago, I told them no problem. It's an SMP on a chip. It runs Linux. It shouldn't take you very long to port your debugger. And then after I left them and they were a little skeptical, I got really kind of inside a little nervous. I just promised something. When I ran into them this week, they were just, I guess they're going to post this in a blog next week, but they told me, they said it took a week to port their debugger and have it up and running and usable. And they said, when they did it for another accelerator, it took a year. And I said, yeah, that's what we're after. Anyways, all these tools you should be familiar with, Xeon and that. Tasking, Jim covered this pretty well. I mainly think of it as you can be operating in a cluster mode and be thinking about MPI and throwing around communications that way, creating the ranks that you want. Steve Scott put a blog out that said a little something about it would be crazy to create a rank on every thread of a Knight's Corner. And yeah, I agree. If you create 200 and some ranks on a Knight's Corner, if it doesn't blow up because you run out of memory or something, I don't think the performance will be very good. I'm not sure why Steve Scott implied that someone would be that dumb, but the cluster model is very real. You can create ranks where you want, do the communication. And then there's this offload model, which it's important to have, and I think it'll have some important usages. I couldn't tell you exactly when to use it. I highly favor the cluster models. I think it's easier to think about because we've been doing them a long time. But offload is there, and that really brings up the offload is a model, that really what this slide says is offload's a model that is familiar with GPUs. So it'll be a model that maps there and is getting some popularity. And then that creates a question. People say, well, what about OpenACC? So for the last 2 years, the OpenMP working group, OpenMP has had a working group trying to look at, can you standardize directives for offload? A good objective. Very, very hard. It's also very hard to standardize a set of directives that don't exist. And so a splinter group off of OpenMP created this thing called OpenACC. It supports GPUs, and it's pretty good for GPUs. It's gotten some good reviews from people that have used it early on at helping them offload in a standard way to a GPU. But a GPU is very different than a Knight's Corner. And they had to, with OpenACC, make a bunch of compromises to make sure that they didn't try to offload a thing GPUs can't run. We don't have to do that with Knight's Corner. You'll find that the offload directives in our compiler are easy to use because you just say offload. Oh, what did I do? I offloaded a multiply nested loop with several OpenMP directives in it. Fine. Oh, I put an offload directive in my main and offloaded my whole program. Fine. You can put offloads wherever you want. Now, I'm not going to tell you which ones will work as well as others because, it depends on your application, but you can offload whatever. You can't do that to a GPU. It's understandable. How do you do a set of directives that can do both? I don't know. We have our Leo. We call it Language Extensions for Offload. It's in our compiler. We'll talk about it later. OpenACC is GPU only. The OpenMP committee has this highly unenviable job, the working group, at trying to somehow reconcile the two and come up with a wonderful standard that'll meet all of our needs now and into the future when it's not even widely used yet. OpenMP 4.0 is probably the join point, and I say that because OpenMP is at 3 dot something right now, and the only way they're going to increment the number to 4 is to add something major. But I actually don't think that's going to happen this year. They were hoping to do it by November, but I have some doubts. The committee will do what the committee does. So anyways, that's a quick blurb on OpenACC. Vectorization. So vectors are getting wider and wider. This is this is a graph that I created of the approximate data width of Intel processors over time since the 4004 and 71. If you take a look at a program as we were looking at yesterday, we could hope that a compiler will auto-vectorize for us, but the language is fighting us. The C programming language doesn't have arrays. It has array syntax. It's just another way of writing a pointer. Pointers are really bad. Pointers can point to anything. Your best bet if you want things to vectorize well is go back to Fortran and quit the C and C++ stuff. But if you're not willing to do that, maybe we could do something. So evil pointers are a problem. Evil pointers are ones that can point to anything, and they confound a compiler. In fact, if we look at this loop clearly just wants to add two vectors together. To us, to the compiler that understands the language, that could do a lot of things. There's an operating system I won't mention that actually does a loop similar to this. It does A sub I equals B sub I, and it walks through. And to initialize a region of memory, they pass in two pointers to this memcopy operation, offset by a byte, and they load the first byte with a data value that they want to replicate, and then they copy. So they overlap. You can't vectorize that. Anyways, the compiler has to assume these can overlap, and because of that, it can't vectorize them. It's just horrible. Even though we look at it and say, well, they're arrays. They shouldn't overlap. So anyways, Fortran got it right. C and C++ with pointers fight vectorization. But let's face it, vectorization hasn't meant much for a while. If you do double precision math with SSE and you get perfect vectorization, the best you're going to do is double your performance. AVX ups that to 4x. Knight's Corner ups that to 8x. 8x is interesting. 2x, not so much. At least not enough to really motivate languages change. Now, if you look with array notations, you know, Fortran 66 had them a little bit. Algol had it. MATLAB has had it in the 70s. And statistical programming languages have had it since the 70s. Fortran 77 allowed array slices on strings. Ada had array slicing. Perl, Python, I use array slices all the time on my Python code. Fortran 90 added it. Fortran 90 is the only one, I'm misleading you a little. Fortran 90 is the only one that really added it for performance. All the rest of them is notation, but it's kind of cool to look. So we had this really radical idea at Intel. Let's add array slicing and array notations to C and C++. Given that they're in like every other language on the planet, this is a really radical idea. This is a motivation behind why we've added array notations into our compiler and why we have added them to an experimental version of GCC. It's not going to take over the world overnight. It's a complicated discussion. I can show you lots of examples where the array notation makes vectorization trivial and writing the program is trivial. But I could also, if I wanted to, show you examples of things we can't do. It can do things like A sub I equals B sub I plus C sub I, lovely. But if you do any sort of cross product, it gets ugly. If you really want to solve that, you need some extra operators like APL, and I don't think we're quite ready for all those operators in C and C++. But we have a tension here between the desire to have an unsafe language with pointers and the desire to vectorize, and C and C++ need to reconcile this at some point. So we've got Cilk Plus. I view it as the array notations as a conversation starter, as a proof point, something we're developing. Would love to have you in the conversation there, but to really properly position why we added them, we're not expecting the world to recode all their programs in it overnight, but we are expecting people to play with it, get feedback, and have this conversation about whether we can do better with C and C++. Because this trend on wider and wider vectors, it's not stopping. It's too obvious of a place to apply transistors. So the fact that just in the last few years we've gone from 128-bit wide to 256 to 512 in Intel processors, and AMD has done the AVX as well, the 256. The AVX encoding itself is pretty obvious that we have the room to bit encode longer vectors in the future. We haven't said anything about products that might do that. We really need the languages to catch up in the practice for that to be practical. Anyways, that's Cilk Plus, a plug for Cilk Plus as a thing. The other thing, if you're really interested in vectorization, I think you should take a look at ISPC, which Matt Farr and what's Mark's last name, do at Intel. But it's this concept of SPMD on SIMD. If you want to send me an email on this, if you can't find it, they had a paper at INPAR a month or two ago that won Best Paper Award. And if you're interested in the topic but not sure you're quite ready to jump in and play with the compiler and stuff, or even if you are, reading that paper, it's one of the most articulate technical papers on a topic I've ever read. It encapsulates the concept of the challenges of vectorization, some of the things you might do, SOA, SOC, or no, SOA and AOS. I love acronyms, but there's too many of them. That it talks about vectorization and some of the challenges there. And this is a project that I think can enter this conversation quite well also. But the way that you're going to get vectorization for the most part, isn't this array notation? It's not ISPC. It's not some extension that's not universally used. It's going to be hoping that the compiler can auto-vectorize, and when it can't, help it. So when the pointers get in the way, when the compiler is a little worried about the language semantics, or the compiler simply doesn't see how to vectorize it, you need to help it. You can help it gently with little hints, like things that say that the parameters aren't aliased and so on. And there used to be, and our compiler still supports something called IV depth, which says, okay, compiler, ignore the dependencies. Turns out that's not powerful enough either. Sometimes there are dependencies that even ignoring that, the compiler still sees reasons why it shouldn't vectorize. And I'm being polite to the compiler. Sometimes the compiler just doesn't get it, and it could have done it. It's very complicated. And other times, the compiler actually sees a legitimate reason you can't vectorize because of the language definition. So we've added this thing called pragma-SIMD, and it is either the most wonderful or the most awful thing in the world, depending on how well you understand the implications. It tells the compiler, vectorize it. You have no choice. And it'll vectorize things. You can have a sub I equals a sub I plus a sub I minus 1. It'll vectorize it. You're not going to get the same answer, but it'll vectorize it. Anyways, we'll talk more about the vectorization and vectorization section, but we've added some neat things to give you a variety. So there's a whole variety of conversation of adding things like array notations and so forth that may be very forward-looking and very powerful to just do it, dang it. All right, so vector widths. Auto-vectorization by the compiler is the most wonderful thing when the compiler can figure it out, but the language is what gets in the way more often than not. Open source, okay. So we did. So if you want to know one web location with a lot of public information, we just created a couple weeks ago, intel.com/software/Mike. And everything I'm going to talk about the next few minutes is actually here if you poke around. So what we did on June 5th is we released a lot of information about Knight's Corner publicly. And I was one of a handful of champions. Jim was another one. And we, so what did we release? We released all the mods for Linux. The Linux that runs on the Knight's Corner card, all the information you need to build that Linux yourself is public. And University of Tokyo is one of many people that have been playing with that for the last year, what they can do with it. I don't expect many users to use this, But if you're interested in it, if we have bugs today that you can't get around, you're welcome to rebuild it. No, I didn't offer to rebuild the kernel for this machine. But it's possible. It's all there. The mods are quite interesting to look at. Of course, we added mods for the longer vector length. We had to do power control. There's a lot you can learn about power control by reading the Linux source that we haven't documented in the higher level documents, but it's really pretty cool. We can play with the voltages and the frequency across the device and so forth, and that's how we do power control under Linux. But the other thing that's really kind of fascinating is we took a simple core. It's actually a P54C design from the mid-90s or late 90s. And we added 64 bits to it. We added wider vectors. We added power control, because power control turns out to be more important today on 60 or 50, 60 cores, whatever, than it was if you were only had one core back in the mid-90s. So we added a bunch of those things. But one of the things that happened as a side effect was the Linux kernel has grown up assuming processors add features monotonically. And so there'd be things in there like, if you have power control, you must have the cmove instruction. Oops, wrong. We didn't put the cmove in, but we put power control in. And the Linux kernel was rife with these if-defs. And they didn't mean to write them that way. It's just always worked for them. And there's a lot of mods that fix and clean up Linux where, because we didn't put all the features in that you might expect. And we didn't put them all in because we wanted to scale. So the turbo boost features on Xeon change the frequency. The hardware controls and does that automatically. And there's no equivalent on the current processor, but software could do the same thing. I don't expect that to be done much because in a highly synchronous program, turbo boost can be complicated. We've seen examples with very well-written MPI code running across the cluster where turbo boost increases the power because it speeds up one core. And when you speed up, you consume more power to get the same work done. But it's done faster, and then you shut down. And the theory is, overall, you save. But if you're in an MPI program and you speed up part of the program, and then you hit a barrier, you increase the power for this processor to get to the barrier, and the other ones hit the barrier at the same power, and when you add up that power, you consume to more power. This is a very complicated discussion. It's not Intel specific, but and so we've had there's a good debate to be had that turbo boost in an MPI situation can not be the best situation. Now, we think we've made some adjustments in our current processors that make that less likely, but because of that reason, I think on Knight's Corner, I'm not a believer that in the time frame of Knight's Corner, we're probably going to vary the power consumption across the whole device. It's possible, and maybe some job schedulers. Maybe you job schedule only on 30 cores and you shut the others off. That's entirely possible, but it would be under software control. Good question. And it's exciting doing new things, and this number of cores on a single device is very new and has lots of implications across software and hardware and programming models that I find really exciting because we'll learn together. We released 3 major documents. The first document, 750 pages long, it's the ISA document. Most of the document is dedicated towards documenting the new vector instructions. We don't document instructions in this manual that already existed in x86. You go to the other document. So it's 750 pages in gory detail of what Knight's Corner instructions look like, including the CPU-IND instruction. And for those of you from Germany, our good friend Andreas Stiller read this thing very carefully the first day it came out and had found things in it that, well, they weren't entirely expected that we were releasing that information, but we did. Nothing really dramatic, but Andreas is, if you know Andreas, he's very good at reading things. So he dropped by at ISC to tell me what he found. He had already written and posted an article. So if you hunt for Andreas, you can see his processor whispers. He loves to read things. So he read 750 pages. The performance monitoring unit documentation talks about what counters there are. And if you're using something like VTune or other things. This document can tell you what you're really counting, what you're looking at, and then an ABI guide. And the ABI guide, we have a different calling convention on Knight's Corner than we do on regular x86 for two reasons. We have 512-bit vectors we had to handle that don't exist in other processors. And the other thing is the processor doesn't support SSE, which is used in the calling conventions of Linux 64 bits. That doesn't have to be permanent, but for Knight's Corner, the ABI document is defined here. But you're going to recompile for Knight's Corner no matter what, because if you're not using the vector instructions, you're not going to get enough performance for Knight's Corner to look interesting. So those documents are all out there too. And TAC had a symposium back in April, and there were a number of papers presented, and they posted them on the TAC website, and some great papers, presentations, and their papers themselves. I have pointers in the same area back to the TAC area so that it's easy to find as well. Oh, all right. Yeah, advertising. I'm not very good at not advertising, but I'll say I just got a note from the publisher this morning that they're FedExing copies of this to my home, which I'll be there in another week. Mike McCool, who's the founder of RapidMine, who Intel acquired, Arch Robson, who is the architect of TBB, and myself are coming out with a book on structured parallel programming. It's not a book about Mike, but it's a book about trying to teach parallel programming without teaching computer architecture. And I love computer architecture, but you don't teach people to write their first programs by teaching them the architecture of computers and then teaching them to write a Java program or something. So parallel programming's never been like that, and I think we need to figure that out. So we've written a book that's based around teaching things like stencils and MapReduce and so forth, and talking about how to do that, mostly in TBB and Cilk Plus. We have some OpenMP and OpenCL examples in there as well. Again, I think it's a conversation starter. I'm hopeful that some people like the book, but I think it's a conversation starter. I know that we need to teach parallel programming differently over time. I'm astonished at how many people jump in learning OpenMP and MPI and learn about stencils later. Yet when we teach programming, we don't start by, we start by teaching Java, unfortunately, but we eventually we catch up and teach things like lists and stacks and queues so that we can have a common vocabulary. And parallel programming, I think there's a good question, what is this common vocabulary we need to teach? So anyways, with that, I think we're going to take a break, and then we're going to come back and do some labs, which is what everybody's just chomping at the bit for. I will emphasize a point from working with customers that just continues to amaze me. We've had a lot of people take their Xeon code, dust it off, go compile it for a Knight's Corner, work on vectorizing, working on scaling. Yeah, you have to work on the memory blocking a little bit and getting the data there, but most of the work is on getting a program that scales and getting a program that vectorizes. And I have seen time and time again Xeon code running this speed, and suddenly it runs this fast on Knight's Corner. And then we like to ask them, well, how fast does it run on Xeon after you did that work? And they go, oh, I hadn't tried that. And they go try it, and it's anywhere in this range. In other words, Xeon is a tough competitor to Xeon Phi. The challenge of programming these devices are getting your applications to scale and getting them to vectorize. And so we'll go back and we'll keep emphasizing those techniques. And it's wonderful we'll have access to Knight's Corner today, but I can't emphasize this I cannot overemphasize this. The challenge here is writing a parallel program. It's not programming Knight's Corner. The challenge is writing a good parallel program. And so we may seem mundane on that, but we'll get to lots of details here. But as you walk away, even if you don't have access to Knight's Corner for a while, go take and worry about how you get things to vectorize and scale, and you'll be well set for this architecture now and in the future.